Okay. So, we write this rocket equation here, and now it is time to start working on this particular equation. So, we have m dv dt plus u dm dt equal to f external. Now, let us first consider a situation where the rocket is moving in free space. Okay. So, in that case, immediately we see that f external equal to 0. And if we rewrite the rocket equation, it will be m dv dt equal to, so there will be a vector term here equal to minus u dm dt. No, so sorry, it will not be a vector equation, because we have already considered the sign of v and u, and we have understood that v and u, they are working in the opposite direction. So, it will not be a vector equation. Okay. So, we write this equation in this particular scalar form, and we try to integrate this. Now, once we do that, we see integration dv equal to minus u integration dm by. Okay. Now, the integration limits will be, let us say initial velocity is v0, and at time t it reaches a velocity v. Initial mass, let us assume to be m0, and mass is m. So, we do that, perform this integration, and we come up with a relation that v minus v0 is equal to minus u ln m by m0, or we can absorb this negative sign to write v, and we can write this as the velocity change. We can call this the velocity change and denote it with delta v, and write u ln m0 by m. Right. Okay. So, this is what we have. This is what we have. This is the final equation of velocity as a function of mass. I mean, it is a function of time, because mass is a function of time. So, we have delta v, the velocity change, as a function of time in the, when the rocket is moving in free space. But when the rocket is not moving in free space, so this is one equation we just keep in mind. Sorry, too high. So, we just keep it here. And we move to our next topic, not the topic, basically next situation, where the rocket is moving under gravity. So, we are assuming vertical, because in principle rocket can go up directly, or rocket can go up in an angle like this or like that. So, but let us, for simplicity, we are considering only pure vertical movement. So, that means rocket is just going under the influence of gravity, let us say from Earth's surface, could be from anywhere. So, in general f external will be given as minus mg. Once again, please understand that we are assuming that rocket is going in the vertical direction, okay, and we are measuring the displacement or velocity starting from the ground level. So, that is why mg comes with a negative sign. Okay. If we set our origin somewhere up in the sky, then this will come as a positive sign, but this is very important. So, this equation will be m, sorry, this m will be a capital M here, because we are using capital M for rocket mass. So, it is m dv dt plus u dm dt is equal to minus m g. Okay. So, if we rearrange this to give dv dt is equal to minus g divided by m minus u by m dm dt. Once again we take this dt here. So, this one becomes dm by m and we integrate. So, 0 to t, v0 to v, m0 to m. Okay. So, it is also another straightforward integration which will give us v equal to. So, I am not doing it completely, but I am leaving on to you. It is a very simple integration, is just the same minus gt or delta v is equal to okay. So, it is just the same as the previous one, but we have additional gt term. Okay. So, we will just keep this also for future reference. So, delta v is equal to u ln m0 by m minus gt. So, that is another relation which we would like to keep. So, this is free space and this is under gravity. Okay. So, we have two situations. Now, before proceeding any further, let us introduce some parameters. Okay. The parameters we are going to introduce, first one is m0, which is already there in these two expression. m0 is the initial total mass of the rocket. So, m0 is given as mf plus mv. Okay. So, total initial mass of the rocket, where mf is the fuel mass, also called the propellant mass. Okay. This is called the propellant mass. You will find this term if you search for rocket motion and other things on internet, or you look into any book. This term is used very frequently, and this is the mass of the total mass of the vehicle. So, what happens is, in a rocket we typically have okay. So, in a rocket which is shooting upwards, so we typically have only a small portion of its total mass, which is, for example, a satellite or a missile, which whatever thing it is carrying in the outer space. Okay. Or yeah, it could be a camera, it could be a satellite, it could be anything. Okay. So, this is called the payload. And so, there will be an empty rocket shell with fuel inside. So, this part is mf, and this empty rocket shell plus the payload is your mv. Okay. So, right now we are not separating in making separation between payload and the rest of the empty rocket cell. We are just considering the whole thing as vehicle mass mv, okay, and the rest of the fuel mass is mf. So, also we introduce a parameter beta, which is called the propellant mass fraction. It is called the propellant mass fraction, which is given as mf by, sorry, not m, capital M, mf by m0. So, this essentially tells us what percentage of the total rocket mass is your fuel. Okay. So, it is mf by m0, and typically I can tell you, I can give you data, I will give you data later on. Typically this quantity is of the order of 80%. So, 80% of a rocket which starts from earth, for example, vertically upwards, 80% of it is fuel, and rest 20% we have a payload and we have an empty vehicle. But these are all typical numbers. It could change depending on how many stages in the rocket you have, what type of payload it is carrying, but typically this is a good number, 80% is a good number. Okay. Now, if you look into it, okay, we can also express this quantity m0 by mv, which is important. We will see why this particular ratio is important. This will be given as 1 by m, sorry, it is simply mf by mv plus 1. Okay. Now, it can be also written as 1 by 1 minus mf by m0, because it will be m0 minus mf, mv by m0, right. Now, this is nothing but your beta. So, we can write this thing as 1 by 1 minus beta. Okay. So, this is also, please remember that m0 by mv is equal to 1 by 1 minus beta, where beta is the propelled mass fraction. So, this is an important relation, we will just keep it in mind and we will use it later. Okay. So, one more important parameter is alpha. What is alpha? Alpha is the loss of initial, it is the mass loss rate, and typically this is given as dm dt is equal to minus alpha m0. So, this is given in the units of total initial mass of the rocket. Okay. So, if the total initial mass of the rocket, let us say 50,000 kg, so alpha is given as something like a second inverse. So, it will be some fraction of this initial mass which will be decayed per second. Okay. Now, if we consider this form for mass loss, then your m will be m0 times 1 minus alpha t. Okay. So, this will be the expression for m0, because if you put t equal to 0, m equal to m0 and t equal to some proper number, then you will get t equal to any arbitrary in time greater than t equal to 0, you get the mass of the total rocket as a function of initial mass. So, using this, we just using this parameters. So, how many parameters do we have introduced? We have introduced essentially 4 parameters. We broke m0 into mv plus mf. We have introduced beta, which is mf by m0. Okay. So, we have introduced 1, 2, 3 and alpha, which is given as m equal to m0 1 minus alpha t. So, if we go back to the free space equation, free space final expression, and try to recalculate, I mean try to use this expression, and we introduce by in terms of this new set of parameters and see what we can get. So, delta V is given by u ln m0 by m. Now, what happens when all the fuel is burned out? When all the fuel is burned out, mf becomes 0. So, the final rocket mass after all the fuel is gone is mv, that is the vehicle mass. So, in order to get final velocity change, let us say it initially starts with a velocity of, I do not know, maybe it can start from 0, it can start from a moderate velocity of 100 meters per second, it can start from a high velocity of 10,000 meters per second, but we are interested more interested into the velocity change. So, the total velocity change, which will be given as delta Vf, for that we have to replace m by mv, that is the final mass of the vehicle once all the fuel is exhausted. Okay. And if you recall, we calculated this fraction m0 by mv, and we have found that this is nothing but u ln 1 by 1 minus beta. So, delta Vf is equal to u ln 1 by 1 minus beta. Same goes for this expression, because this part is identical in this too. So, for rocket motion under gravity, we can have a similar expression of delta Vf, only thing is we will have a minus g T f on it. Okay. So, when we are considering rocket in free space, the final change in velocity is given by u ln 1 by 1 minus beta only, and when we are considering gravity into this equation, so we have an additional term of minus gt here. So, we have to put t equal to Tf in order to get Tf. Tf becomes the time of flight, the total time for which a rocket can fly using its fuel. Okay. Now, it so happens that Tf is also we can also calculate Tf from this expression, because if we put t equal to Tf, m should be equal to mv in this expression. Okay. So, if we put mv by, if we put mv here, so we have m0 1 minus alpha Tf, and mv by m0 is equal to 1 minus alpha Tf, which is once again is given by, what is this expression? If you recall, it will be simply 1 minus beta, right. So, that gives us Tf is equal to beta by alpha. Okay. Fine. So, if we do that, if we put this expression of Tf here, so our time of flight is given as beta by alpha for motion under gravity. Now, this is a very interesting result, because when we are not considering gravity, it does not matter at which rate the fuel is exhausted, but we finally get the same change in velocity. Moment to introduce gravity into the equation, the rate of fuel exhaust is also becoming an important parameter, which was previously not there. So, you see that in free space does not matter if you move slowly, I mean by exhausting less amount of fuel, or you are moving fast, you essentially end up having the same velocity, total velocity change for the fuel available. But when it comes to, when we have a gravitational pull available, gravitational pull into this equation, it is also important at which rate you exhaust this fuel. And what was the propelled mass fraction? So, there is a competition between this and this. Okay. Fine. Now, let us. So, we would like to have an expression for the velocity, for the distance traveled. So, in order to get this expression, we go back to this basic equation and we just replace F external as minus mg, and then we try to integrate it, and we have already done that, which gives us delta V is equal to u ln m0 by m minus gt. So, this is the exact same expression which I wrote here. Now, what we do is we introduce, so we move V0 to this side, and instead of writing V, we write dz dt. Assuming that the rocket is moving, let us say this is your rocket, which is moving along the z direction. Okay. V is written as dz dt. So, what we are looking for is so far we have calculated the velocity change, and now we want to gain an expression for the total change, total distance covered by the rocket under the influence of gravity. Okay. Now, in order to do that, we have to perform this integration, which will be integration of dz from, let us say the rocket starts from the ground. So, at time t equal to 0, z equal to 0, it becomes z here. So, you have V0 integration dt, it will be 0 to t minus g t dt 0 to t plus u integration ln m0 by m dt. Okay. Now, first term is straightforward, it will give you V0 t, second term is half g t square, third term we have to manipulate, once again it will be from 0 to t, 0 to t. So, we have to write m, the expression for m as m0 into 1 minus alpha t. So, m0 will cancel out, you will essentially have ln 1 by 1 minus alpha t dt. So, this is a slightly tricky integration, but it is completely doable essentially. Oh, okay. So, what we can do is we can simply put a minus sign here, and we can, instead of writing it like this, we can write 1 minus alpha t. So, that is even easier to integrate, and once we do the final, perform this final integration, I am not showing it, you can do it yourself, you know how to integrate these things. The final expression for z will be V0 t minus half g t square minus u times t. So, there will be an ut term coming up, okay, and there will be a minus u by alpha into 1 minus alpha t ln 1 minus alpha t, right. So, this is the final expression for z at any given time t. Now, in order to gain the maximum height which can be achieved by this, which can be achieved by the rocket, we have to put t equal to Tf, which is equal to beta by alpha. Now, if we do that, we So, if we do that, we immediately see Z f is equal to V 0 beta by alpha minus half G beta square by alpha square plus U beta by alpha minus U by alpha 1 minus, so beta by 1 minus beta ln 1 minus beta. Okay. So, this is the expression, and if we take beta by alpha common, so we have V 0 minus half G beta by alpha plus U minus U beta, no sorry, U by beta minus beta. So, this is the expression for maximum height achievable in terms of the parameters. So, if we put V 0 equal to 0, the initial velocity if we put at 0, then this one gone, beta by alpha. So, essentially what parameters do we need? We need beta, we need alpha, and we need U, that is it. So, all and G of course we know, G at earth surface, and if we know the value of V 0 is 0, otherwise we can assume that it to be equal to 0. Okay. So, essentially we need V 0, G, beta, alpha and U, these 5 parameters, and we can give you the final velocity of the rocket final velocity of the rocket, or and we can also give you the maximum height that can be achieved by using this particular rocket.